Okay, last time we discussed, or I already explained about the similarity between the water and the electricity, such that we mentioned last lecture, okay, pipelines similar to wires, water, electrons or charge, flowing water, like flowing electrons, or in other words, electrical currents. Pressure is voltage, the voltage. So how about this system? This is water pump example. We have a water here, a water pump, which is a pressure source. Then the water will flow from the pump to the turbine or water wheel. Then the water wheel would make some resistance for the water. So it will start rotating. Then the water will flow back to the pump and so on to complete the cycle. So what's equivalent to water pump in electricity? Water pump, which is similar like water pressure source. What's the equivalent to this? I guess?
Battery.
Battery, yes. Or in other words, I would say voltage source. So the general meaning, which is we say voltage source. Or battery, whatever. Then we have water pipelines, the pipeline. So what's the equivalent for it? Wires, right. Then we have a water wheel or turbine, which is making some water resistance. What's the equivalent to it in electricity? Resistor, correct. And we have the water is flowing here. What's the equivalent to the water flowing? Currents. So that's it. That's the similarity between them. So you can imagine that how is the electricity flowing? Similar way, and how is the water flowing? We have a pressure source, or like a water pump, or we call it electrons pump or electrons pressure source. Then it will provide some electrical currents, so they will move toward the load, which is that makes some resistance, like the turbine. That's one example. Okay. Now, let's assume this scenario. I'm going to assume the same example. We have a water pump. And I'm going to make a wheel turbine. But I'm going to stop like this way, make it open. In this situation, no matter if the pump is giving pressure for the water pressure, do you think the water will flow? No. Why? It's open loop, no closed path, right? So the equivalent this in the circuits, which is we have a voltage source, we have a resistor, then it is open like this. So do you think there will be a current? No, because it's open circuits, right? So that's how we can figure it out. That's one way. Other way, let me draw the same example. Here is the turbine. And now it is, I'm going to assume it is open. Closed path. Like this way. Now it's closed path, it's not open path. But do you think the water will flow? No. Why?
There's no power source.
No pressure source, right? Nothing to motivate the water to flow. So this is equivalent to this way. We have R. So here the voltage is 0, right? Therefore, the current will be 0. So we can conclude two important things that must exist to the current to flow. We need to have two important things. The first thing, we need to have a voltage difference. The second thing, we need to have a closed path. Okay? These are very important, these two conditions. So I would say two conditions to the current to flow. We have the first thing, the closed path. And the second thing, we have what? We need to have a voltage difference. If these two meet, then there will be a current to flow. Otherwise, no current will flow. Then the current will be zero. So this means sometimes we can see a voltage, but we cannot see a current. The voltage can exist no matter what it is, unless there is no short circuit. But the currents need some conditions. Needs a closed path, needs what's called a voltage difference. One example of this, I used to talk a lot about the wall utility outlet. So we have a wall outlet here. There is electricity on it. How? Bring a digital multimeter and make some measurement, and you will see there is some electricity. I mean, there is a voltage reading. That's the right meaning. So the voltage reading, you will see it's 120 volts, something like that. Then there is electricity. But why there is no electrical currents? Because there is no closed path, something to complete the circuit. How you can make a closed path? By connecting your cell phone charger or connecting any other load like your laptop charger, whatever, any electronic device. When you connect this to the plug, then you are completing the circuit. So you can notice that when you are connecting the plug, there are two slots. Then when you enter these two, you are completing the circuit. Therefore, the current will flow from the plug toward your device. That's how the electricity flows. Now, how about if I disconnect the electricity, disconnect the power from this, for example, this building, or then you are connecting the device, but there is no power, there is no current will flow. Your cell phone cannot be charged. Why? Because there is no voltage difference. The voltage difference comes from the wall outlet. Okay? So these two conditions must meet for the current to flow. Any question about this example? Okay, so I consider this example as very important for you to understand how is the electricity flowing. Because most likely the electricity is something hidden, something happening inside the wires that we cannot see it. But when you imagine this like similar to water, then it will be clear. Now, let's go to another definition that we heard about this a lot. Power. What does power mean? And there is something else that we used to hear about this, which is energy. What's power? What's energy? What's the difference between them? Or what's the most important thing? So any thoughts about the power or the energy? What's the difference? Okay, so mathematically, the power is the time derivative of the energy, or it is the multiplication of the voltage times the currents. That's in math. Now let's go to the concepts. The concept is energy is related with time. So I would say I consumed energy like, let's for example, I consumed 1,000 joules alone without mentioning the time. This is incomplete answer. But when I say I consumed 100 watts, this is complete answer. How? Watts means how much energy you are consuming per second. How much energy per second. While energy means how much energy that you are consuming alone without mentioning anything. This is very similar in concept to speed and distance. So when you are driving and you say like, I drive with speed 70 miles per hour. Okay, this is complete information. I know that you were driving with 70 miles per hour. That's complete information. But when you tell me I drove around 1,000 miles, okay, so I'll say, did you drive 1,000 miles per day, per week, per month, per year? It's still incomplete, right? Then the same for the energy and the power. So when I say like the energy, similar when I say to the speed, I'm sorry, energy to the distance. So when I say like I consumed 1,000 joule, okay, is it 1,000 joule per second, per hour, per year, per week? Or when I say like I consumed 50 watts or 100 watts, okay, I know this is joule per second, okay? So watts, again, the unit of watts is similar to joule per second, which is the speed, okay? While, I mean, mathematically, you can say the derivative of the energy with respect to the time, the same when we say the speed is the derivative of the distance with respect to the time. And in other words, we can say voltage times the current, V times I. Okay? Now, I have a question, another question. When we pay for the utility outlets, do we pay for energy or do we pay for power?
Energy.
Energy, why?
This is power over time.
Yeah, or we would say like we are paying the power utility, for example, we are paying for a month, right? Like for example, monthly, you will get the bill, that's what you consumed for a month, right? So it is what's energy. But the question is, when you look at the units, or like when you look at the utility bill, for example, you consumed during that month as 500 kilowatts hour. So we see it in watts. So what's the problem? Is it really power or energy? The power in watts, energy in joules. So what's the problem? Is it really power or energy? Do we pay for power or energy? Energy.
Power by time.
Yes, there is a time. Basically, how we can recognize this is we will say watts equals joule over second. Okay? Now, joule will be watts times second. Okay? Then let's multiply or let's divide 3,000 because we know hour equals 3,600 seconds, right? So try to divide by 3,600 both parts. So here it will be like watts times, so second will be hour over 3,600. Okay, it will be times hour over 3,600. Okay? Now we need to make it kilo. We know 1 kilo means 10 power 3. So you need to divide by 10 over 10 power 3. So joule will be kilo watts hour times 1 over 3,600 times 1 over 1,000. So we notice that's kilowatt hour. That's what we pay for the utility. So we are paying for kilowatts hours. So we will realize that kilowatts hours, it's another unit of the energy. The energy can be in joules. Kilowatts hours is still energy. And the same thing if you heard about BTU. Also, it's also part of energy. So it can be different units. So that's fine. Again, so what we are paying for our utility bill is the energy. I mean, again, and it makes sense for us. We are paying for the energy because the utility bill that we are not paying per second. We are paying, for example, per month, something like that. Okay? Any question? Okay, let's talk more about the theoretical parts in power, which is some elements. So as we know, for any elements that we have something to supply, something to consume, right? Or something to absorb. So when we connect your cell phone to charge your cell phone, the bulb light is supplying power, your cell phone is absorbing power, right? Then the same way for any other devices. In order to maintain a power balancing, we need to have something to supply, something to absorb. Now, let's assume we have a box, and I don't know what's inside this box. Is it a source? Is it a device? Let's assume we have something like that, this box. Now, I need to know, is this box supplying power or absorbing power? We have some assumptions in electrical engineering, then we can know if this element is supplying or absorbing by looking at the voltage polarities and current directions. So there must be voltage polarity for every device, and there must be a current directions. How? I will say this element is absorbing power if the current enters the positive polarity of the voltage. Positive sign of voltage. And I would say the element is supplying power if the current enters the negative sign of voltage. Now let's look at this one. Locate the currents. Here is the currents. Here is the current sign, the current direction, and this is the voltage sign. So the currents, current direction, and let me change the color. This is the voltage polarity. The current enters the positive, right? Therefore, this element is absorbing power. So I will say this is P absorbed equals V times I. Okay? Is this clear? Now, how about the other thing? The other one, this is the voltage polarity, and this is the current direction. So since the current enters the positive, or it's leaving the positive, or in other words, I will say the current is flowing here, then it will enter the negative, right? Since the current enters the negative, this element is supplying power. Okay? Now, is this clear? How can I know if this element is absorbing or supplying? By looking at the voltage polarities and current directions. If the current enters the positive sign, then it is absorbing. If it is entering the negative sign, then it is supplying. Okay? And you can imagine this by assuming a small circuit. Here is a voltage source, here is a resistor. So the voltage source, this plus minus, the current will go out from the positive, then will enter this resistor. So this resistor should absorbing power, and that's right. Why? Because the current enters the positive, right? So absorb. And here the currents with regarding to the source, it is entering the negative, therefore this is supplying power. Okay? Is this clear? Good. Now there is something else. Let's look at the absorbing power alone. Now with the absorbing power, we know this element is absorbing. If for example someone asks you, what's the supplying power for this? I mean, we know it's absorbing, but let's calculate the supplying power. So what should I say? It's not supplying, it's absorbing. Then what should I say? What should I write in this value? Let's recall when we discuss about the vectors. So we say the vectors, when we have the opposite of our assumptions, we will put a negative sign, right? So that's happened for the voltages, the currents, and the power. So what we have here in this situation, we realize this element is absorbing power. But since it keeps asking me what's the supplying power, so I will say the supplying power equal to the negative of the absorbing, then which is going to be negative V times I. Okay? So we will put the negative sign. Then, when you look at the answer and see a negative sign, you will say, okay, what we have in the reality is the opposite what we have here. So whenever you see, look at the power and let's see, like, you read any label or like read any example and see the volt or the power absorbed of this element is negative 100 watts. Then you will keep in mind, it says the negative power, the power absorbed is negative 100 watts, therefore the supplying will be it's supplying power, not absorbing. Because the negative sign means the opposite. Now, how about the other thing? I know this element is supplying power. Now I need to calculate the power absorbing. So the power absorbing, since this element is supplying while I need to calculate the absorbing, this is the negative sign of the supplying. Therefore, it will be negative V times I. Okay? So these elements are understanding the absorbing and the supplying something crucial, something very important, because we need to use it for the rest of this course. We will not use it only in today's lecture or in the quiz or the other things. So we will use it later when we discuss DC, when we discuss AC, three-phase. So supplying and absorbing something very essential, very important to understand. Any question about supplying and absorbing? Okay. Now let's see this example. We have this diagram, and assuming the following information, assuming we have VAB as 10 volts, and we have the current I equals to 2 amperes. And we need to make some analysis, like VAB, here, the positive at A, the negative at B. So again, VAB equal 10 volts. I equal 2 amperes. I just repeat them. Then, when I say I, AB through element E, what do I mean by this? I say I need to go from A to B, travel through element E. What's the current will be? So I'm traveling clockwise. And the current I is going clockwise, right? Therefore, it will be the same as the current I, which is 2 amperes. While when I say I, BA through element E, I need to travel from B to A through element E, which is I'm going counterclockwise. Therefore, and the current is actually clockwise. Since it's opposite of my assumption, I'm traveling counterclockwise while the current going clockwise. It's the opposite of my assumption, so I will put negative I, negative sign. Then it will be negative 2 amperes. Again, the negative sign means it's the opposite direction. Then, how about if I say calculate VBA? The positive must be at A, the negative at B. But when I say VBA, which is the opposite of VAB, so it will be negative VAB, then it will be negative 10 volts. Okay? Clear? So that's simple. Now, let's go to another, the same example, but with more details. Let me give you some time to write, and we will go. Okay. We still have V equal 10 volts, I equal 2 amperes. Now we need to calculate several things. So the first thing is the voltage drop from A to B. The voltage drop from A to B. Now let's recall the drop and the rise mean. Drop means traveling from positive to negative. Rise means traveling from negative to positive. Okay? That's what you need to know. Now, The question says the voltage drop from A to B. Again, drop means travel from positive to negative. Now, am I moving from positive to negative? A to B? Look at this one. A is positive, B is negative. Am I moving from positive to negative? Yes. So which is the same as my assumption. Therefore, this is going to be equal to V, which is the same as 10 volts. Okay? Now, the second one, which is the voltage rise from A to B. Rise means traveling from negative to positive. Now, when I go from A to B, am I traveling from negative to positive? I'm traveling from A to B. Am I traveling from negative to positive? No. Therefore, it's the opposite of my assumption. Then it's going to be negative V, which is negative 10 volts. Okay? Now, the third one, the voltage drop from B to A. Drop, again, means traveling from positive to negative. Am I traveling from positive to negative when I move from B to A? No, because I'm moving from negative to positive. Therefore, it's going to be negative, right? Because it's the opposite of my assumption. Negative 10 volts. Now, the last one about the voltages, which is the voltage rise. Rise means traveling from negative to positive. Now, when I move from B to A, move from B to A, are you traveling from negative to positive? Yes. Therefore, it's going to be positive V, which is 10 volts. So you see, they are all 10 volts, 10 volts, 10 volts, but the things which matters with us, the sign. Okay, if it is the same as our assumption or opposite of our assumption. Now the next one, the currents the currents from A to B through element E. Now I need to travel from A to B through element E. So I'm traveling clockwise. The real current direction is clockwise, right? So it's the same as my assumption, right? Then it's going to be the same as the currents, which is I, then it will be 2 amperes. Now the currents from B to A through element E. Now I need to go the opposite way. I need to travel from B to A. Travel from B toward A through element E. Now, I'm going counterclockwise. The real current direction is clockwise, right? So it's going to be I, negative I, because it's the opposite of my assumption. Therefore, negative 2 amperes. Okay, does this make sense? Now your turn, the current from A to B through element S. What do you think? You can try it by yourself and tell me the answer. You need to travel from A to B, but through element S. Travel from A to B through element S. So what's the current will be? Negative I. Why? Yeah, because the opposite. When I go from A to B through element S, I'm going counterclockwise, while the current is actually clockwise. Therefore, it is going to be negative. How about the next one? From B to A through element S. How will it be? So I'm traveling from B to A through element S. It's going to be positive because I'm traveling clockwise, and the real current direction is clockwise. Okay, so it's simple. Now, we need to calculate the power absorbed by element E. the power supplied by element E, absorbed and supplied by element S.
This.
Okay, before answering these questions, we need to determine which item or which element is absorbing, which element is supplying. So what I encourage you to do is taking each part alone. So I'm going to take element S alone. Here is S, here is I. This is plus minus V. And I'm going to take the other element alone. Here is E, here is plus minus V, and here is element I. So when you look at this element, you will see the current is traveling this way, traveling this way. So for element S, the current enters the negative. For element E, the current enters the positive, right? So what does this mean? The element S, since the current enters the negative, then it is supplying. While the element E, it is absorbing, right? So I will say the power supplied will be V times I, which is 10 times 2, then it's going to be 20 watts. That's for element S. How about the power absorbed by element S? It will be the negative of the supplied element S, which will be negative 20 watts. Okay? Because we realize it's supplying. If we need to calculate the absorbing, just put a negative sign, because absorbing is the opposite of supplying. How about this element here, element E, the power? It is absorbing power. We define absorbing, so the power absorbed by element E equals V times I, which is 10 times 2, then it's going to be 20 watts. While if we need to calculate the supplied power by element E, it will be the negative of the absorbed by element E, so it will be negative 20 watts. Okay? Any question? Let's go to the substitutes, the values. The power absorbed by element E. So here is absorbed by element E, this is 20 watts. That was the first one. The power absorbed by element E. The power supplied by element E, negative absorbed, negative 20 watts. The power absorbed by element S. Let's go to element S. And we know that the power absorbed by element S, negative 20 watts. Negative 20 watts. The power supplied, which is the negative of the absorbed, then it's going to be positive 20 watts. Okay, let's make it like this so you can write. So that's simple. So what I encourage you again to do is you can look at every element, then you need to determine is it supplying or absorbing, then calculate the corresponding power with it. If it is supplying, calculate the supplying. If it is absorbing, calculate the absorbing. Then you can say the other one is the negative. After that, look at what you need to answer in the question, then you can answer. Now I'm going to write some textbook problems because this is the end of chapter 1. Textbook problems 1.12, 114, 116, 118, 120. So I encourage you to try those before Wednesday quiz. Okay, so if you understand them, then of course definitely you will get 10. The quiz will not be difficult. It will be something similar to this example, or maybe less easier than that. Okay, any question about chapter 1? Okay, let's start chapter 2. By the way, if you need the notes that I wrote, you can send me an email, then I can provide you the OneDrive link, so you can have access to the written notes. But anyway, you already have the completed notes, so I don't think you need it. But in case if anyone interested, I can provide you the OneDrive link. Okay, chapter 2 is related to the circuits, some basic laws of electrical circuit analysis. So before going to the circuits, we need to know the elements associated with the circuit. Again, like before creating some words, we need to know first the alphabets. So there's something we call it circuit elements. After knowing the ABCs, then we can create some words, which is solving some circuit analysis. After that, we will make these words and combine them to be a useful sentences, which is the applications of the power, or the application, I'm sorry, not the power, electrical engineering. So as an example, as I mentioned last lecture, like the motors, we can model it to be a combination of resistors and inductors. The power lines, we can model them to be the part of capacitors, inductors, something like that. Any other devices, we can model this. So basically, what we used to do in the electrical engineering, we used to look at the system that we need to do, like control or do some techniques on it, or applying some electrical things on it. So the first thing is we're trying to model this to find something we call it electrical model. But which is the electrical model will be a combination of electrical circuit elements. Then, after modeling this, we can make some circuit techniques, some circuit analysis. So sometimes the models, the equivalent model, does not exist in real life. You cannot isolate these elements, but you will say that's something equivalent to this. Okay? Now, some ideal circuit elements, that's what we will cover in this course. So the first important thing that you need to look at, which is ideal circuit elements. So the word ideal, this is in purpose. So ideal, which is different than practical. This is different than practical. And you will see some electrical circuit elements in the textbook that we will not cover in this course. So in this course, I want to make it easy for you because, again, it's fundamentals of electrical engineering. It's not electrical circuit analysis. So I use the simplest way. So we will just go through a small or some simple elements. We will not go for very deep details. So when we discuss about the power, we said there is supplying power, there is absorbing power, right? Therefore, there should be two elements, or two group of elements. The first group of elements, which is some elements that are supplying power. The second group of elements are some elements that are consuming power. Therefore, we have the first group here, which is sources. Okay, of course, sources are used, or the main reason for the sources are supplying power. Then we have passive elements. What does passive element means? Every time when you see the word passive elements in electrical engineering, this means the element that are consuming energy. Or in other words, they cannot produce energy. Any element that cannot produce energy at all, this is considered as passive elements. One example of it, the light bulb, is passive elements. There is no way for the light bulb to produce energy. Then when you have the motor, it's passive elements, cannot produce energy, something like that. Some other elements, any element that are consuming energy are passive elements. While there are some elements that can produce energy, like battery is not passive because it's producing energy, or it can be a source. Even though sometimes you need to charge the battery, but at the same time you can take some energy from it, it can produce energy. So anyway, passive elements Whenever you see the passive elements, this means any elements that are consuming energy or they cannot produce energy. So let's go to the sources. We have the ideal voltage source. We have something also called ideal current source. So the word ideal, again, is very important. In the textbook, you will see some practical voltage source, practical current source. This will not be covered in this course. So ideal voltage source, like a battery, ideal voltage source, or sometimes we prefer to use any voltage source, not only battery, like this way. So by looking at this symbol, you will see only a voltage, and the voltage polarity is given. So this voltage source provides a constant voltage, while ideal current source provides a constant current, and it will look like this. I'm not sure if you have ever heard of this from physics, but here, this current source, the element that's providing a constant current, but the voltage can be changed depending on the load. While the voltage source is the element that's providing a constant voltage, while the current can be changed depending on the voltage. So, current source, constant currents. Voltage source, constant voltage. Okay? Now, what's the physical meaning of this? I mean, yes, this is theoretically, we have voltage source, current source. How can we find this in real life? Where can I find voltage source in real life? Where can I find current source in real life? Actually, the vast majority of the elements that we have are voltage sources. However, we have we have many current sources, but the vast majority are voltage sources. What's an example of voltage sources? What do you think? The battery, right? Most likely, when you look at the battery, you will see constant voltage, right? 12 volts battery, 5 volts battery, 9 volts battery, even like small batteries that you are using in small devices like 3.3 volts battery, right? So we have multiple batteries, and all of the batteries providing a constant voltage, right? How about the wall outlets? Is it voltage source or current source? Voltage source. Why? We used to say 120 volts, right? So it's voltage source. Okay, so again, the vast majority of the applications or that which we have are voltage sources. Okay, is there anything as current source? What's an example as a current source? Okay, I can give you some demonstration example, like for cell phone charger. So as we know, for the cell phone charger, especially with the fast chargers, like previous I think last 6 years, we start seeing the fast charging technology, right? So the fast charging technology, it will move your cell phone charging from 20% to 80% within, I think, 30 minutes, or 20 minutes, something like that. Then, after that, after 80 seconds, if you're still using the fast charging, but to reach from 80 to 100, it might require another 20 minutes or require 30 minutes. So what's the point? It's still fast charger. The point is the charging methods. So actually, the fast charging works only until up to 80%. Some cell phones 85%, depends on which manufacturer, but to reach this point. So that's the fast charging period. While after this 80% or 85, whatever, then it will be in another charging method, which is even if you bring any other charger, it can be fine, no matter if it is fast charging or not. Okay, so what's happening? Actually, during the fast charging method, or below than 80%, we charge the batteries by making the charger as current source, by providing a constant current. So in the all chargers, let's for example, I'm talking about like the iPhone, all charger iPhone, it's constant current, it provides only 1 ampere to charge the battery. While the fast charger can provide 3.3 amperes, or sometimes 5 amperes. So which is maybe 3 times faster or 5 times faster. That's why it will be faster. So during the charging transients, up to 80%, this is working, the charger is working as constant currents, as a current source. So the charger equivalent model for the charger will be a current source. Then after switching from 80% or after switching that, it will switch to be a constant voltage. So it will be charged based on the voltage, not based on the current. So whenever we have a constant voltage, most likely the charging method using a constant voltage will be slower than what we have the charging for a constant current. Okay? And why we switched this, why we didn't use constant current and that's it until reaching 100? Most likely this is related to the lifetime of the battery. We don't want the battery to be overcharged, and also the chemical materials also of the battery, we don't want this to be affected. So they realize the optimum is to reach at this percentage, no matter whether it's 80 or 85 or 90. To reach this percent, then after that, we'll start charging this using the different charging method. And even though it's highly recommended, when your battery reaching to this situation, it's highly recommended to not charge it up to 100%. That's fine. Like when it's reached 80 or switch to the other charging method, to maintain a good life cycle, just you don't need to make it to 100. Unless you have some other work to do or traveling, then that's fine. I mean, it will not be harmful a lot, but I mean, during the daily usage, it's not recommended to make it up to 100%. At the same time, it's not recommended to make it below than 20% because we don't want to go something called deeply discharged. This is another topic that's related to the batteries, but this is for your information. If the battery reaches something called deeply discharged, which is turned off, no power, this will affect a lot in the life cycle of the battery, and this is not highly recommended. Okay, anyway, let's go back to our topic, which is we have sources and we have elements that are consuming energy. So the passive elements can be resistor, inductor, capacitor. Resistor like this, simple, R, the unit in ohms. Inductors like this, simple, L, the unit in Henry. The capacitor, C, and the unit in farad. I think you are familiar with this from physics. But anyway, let's talk a little bit about inductor and capacitor or resistor. Resistor are the elements that are energy will be dissipated. For example, the light bulb. The light bulb, the energy will be dissipated as light, dissipated as heat. So when you touch the light bulb, it will be warm. So this is resistors. We have inductors and capacitor. The inductors, the energy is stored as magnetic field. The capacitor, the energy is stored as electric field. One example of the inductors, like the motors. The motors, you will see some residual energy in the motors. Also, for example, the motors, the startup of the motor will take a lot of electrical current, a lot of magnetic field with this. So that's why sometimes when you turn on the motor, if you have a large motor, you will see a light flicker because it will absorb a lot of energy. Even if you are connecting a generator, if you have your own generator, and connect a large motor, you will notice the generator sound, then it will go back to normal because it's absorbing a high amount of energy. And this high amount of energy is magnetic. Goes a high amount of currents as magnetic field. Then another example of capacitance is the power lines. So the power lines has equivalent capacitance with the ground. So when you go close to the power lines, sometimes if you are not in safe distance, you will get shocked. Why? This is because of the capacitance effect of the power lines. Because even if you are not touching the power lines, especially I'm talking about high voltages like 400 kilovolts, 500 kilovolts, 132 kilovolts, this will be dangerous if you go close to power lines, not only touching them. That's some examples. Next lecture, we will go through in details about the relationship between resistor, inductor, capacitor. So see you in Wednesday.